Okay, so hi, good evening, everyone. So welcome back to Plan 258. Okay, and this is our agenda for today. So we discuss about game theory, yeah, uh, non-zero-sum strategy games, and this is the topic about threat and credibility. So this is kind of application of this, and uh, and then we talk about game of trust or harmonic game. Okay, so and this next week we'll discuss about the others topic. And okay, so Andrew, I have your email, but I deliberately did not answer because we can discuss it next week when we discuss the group decision. Okay. Okay. So okay, before we start, okay, do you have any question about last meeting solution of zero sum game? Can you see my slide?
Yes, sir.
So, one thing I want to discuss is the almost the last part of this, which is the this one. Okay, so given this game matrix, okay, clearly this is zero sum because we have only one number in each cell. Okay, can we try to compute this in the game theory calculator? And then can you find the R? Okay. And then can you also try other numbers? Yeah, this one and this one. So three practices. Okay, and record the odds of the three practices. This one. Okay, and what will be your conclusion? Can you try? So if we have this number, so I will put the game theory calculator here. Can you see? Yeah. So we have here we put 8, right? And then 1, and then here is 4, and then here is 6. Is that correct? And this is zero sum, so you click this zero sum and then click the blue one. Okay? And then you will get the answer down here. There. Yeah. So this is the R. So for the row player, you have this part. Let's copy this and put into a notepad. Yeah. That we will know. Let me open notepad. So I put it here. Yeah, as a notepad. Okay. And then go to the next one. Yeah. And put this into the calculator also. Mm. So let's put that. So here we have 11, 4, 7, and 9. Yeah, so this is zero sum and with this one. And if you look at the answer, exact, yeah. But the game value is different, yeah. But the art is the same, isn't it? Hmm? Uh, the art is exactly the same, yeah. So the values are different, but the art is the same. Why? Okay. And then go to the next example here. So again, we input this into a calculator. Okay. So you have 16 here and 2, right? And 8 and then 12. Okay. Again, if you click the blue uh, triangle, you can get the result here. Again, the result is exactly the same in terms of the art. Yeah, but the game value changed. So what can you conclude? Uh, can you open your camera so that I can see you? So what can you conclude with that? So if you look at the pattern, yeah, the art are all equal. Yeah, is it happen by accident or not? Yeah. And look at the numbers. Yeah, uh, and this one is 2/9, right? The art is this one is 5/9. Yeah, 4/9. This is 7/9. Those are the art. So, but if you look at the number here, this one is like multiplied by 2, isn't it? Yeah, 8 and 16, is that correct? And then 1 and 2, so multiply by 2, yeah. And here, you just add with 3, is that correct? Yeah. This is how you see the pattern, okay? So 8 plus 3, 11, right? 1 plus 3 becomes 4. 4 plus 3 becomes 7. So all the cells are multiplied, yeah, by 2, and this one is add with 3. Is that correct? Okay, so if you notice that that's called scaling, right? So the R are equal, yeah, they are not by accident. Okay, so the because these numbers represent utility, okay, preference, right? So then you can multiply, you can add as long as the order is the same. Okay, so the art will be the same. Of course, the game value change because the number change. Can you see the characteristic of this? Yeah. So that means the game is not affected, yeah, by adding a constant or by multiplying the payoff. Yeah. So remember this now. When you face any game matrix, yeah, in game theory, remember this characteristic. Okay. Okay. So of course, because you see they are not the same, but the game value of course change. Yeah, because we do exactly scaling, yeah, by adding or by multiplying. So with the exact scaling, yeah, then you can get the same value, yeah, when you multiply or you add. Okay, yeah, that's the thing that we need to discuss on last week uh, discussion. Yeah. So is there any question about this? Yeah, this is just the conclusion of that. Right? So yeah, you can check the others. So if you want to get the art, okay, when the size of the matrix is not 2 by 2, and not 3 by 3 or whatever number, then you need to use linear programming. Yeah. Anyway, I already developed calculator for you, so you don't really need. Inside that calculator, have linear programming. Yeah. So then you don't need to worry about this anymore. Okay. That's what we need to discuss about that last week meeting. Yeah. But we did not take it. Is there any question about that? If not, so let's go to the actual discussion for today. This is heavy. Yeah. So let's discuss about what is called non-zero-sum strategy games. Okay. Can you see the slide? Okay, so you can follow this by downloading the updated slide in Moodle. Okay. I just updated today. So if you download last week, so you need to download again. Sorry. Okay. So in this lesson, you will learn non-zero sum strategy games. Yeah. Uh, Zero sum mean in each cell, okay, the payoff between each player, the sum is zero. Okay, so here the sum is not zero. So you can see the characteristic, yeah, the number in each cell is not just one, but more than one, yeah, depending on the number of players. Okay, so let's discuss two players as simple, yeah. And at the end of this lesson, you have assignment in Moodle. Okay, it's about traffic. Okay, so we will discuss three techniques, yeah, iterative domination, Pareto optimal, yeah, and Nash equilibrium. Okay. And I will connect this to transport planning. Okay, so we are talking about strategic games. Okay, so we have what is called non-cooperative. Yeah, so strategic game is basically non-cooperative or competitive games. Okay, so the positive payoff of one player means negative payoff of the other, but because this is non-zero sum, so not necessarily equal payoff. Okay. Uh, Even in competitive games, yeah, you can have a conflict or no conflict. Yeah. So yeah, this is zero sum. Okay. So you will see only one numbers in itself. Okay, because zero sum means the payoff for the row is the same, exactly the same, and negative payoff of the column. So in that case, you don't need to write two numbers. Yeah, one number is enough. Okay, so in zero sums, okay, you this is very strictly competitive game. So for example, in the sport, if one winner, the other one will lose. Okay, so in zero sum games, you will see that the maximin is exactly the same as minimax. Yeah, this is the saddle point of the equilibrium. Okay, and if you inform, yeah, your strategy to your opponent before you play, you will not gain any advantage or disadvantage. Yeah, but this is different. Yeah, in non-zero sum game. And so non-zero sum game is more interesting and more general. Yeah, therefore, sometimes information may have affect the outcome. Okay, and a joint plan of action or communication prior of the game has no benefit, yeah, in zero sum game. So in contrast, okay, so say you have two players, Mr. Row and Mr. Column, in this case. Uh, so This is an example of zero-sum games with Miss Row have three strategy, A, B, C, and Mr. Column have three strategy, D, E, F. Okay, so then we have in each cell here, the payoff matrix, we have two numbers, and because two players, we have two numbers. So the first number represents the row, the second number represents the column. Okay, so this is the payoff of the column. So what's the meaning of negative 1, 1 in here? That means if Miss Row play C and decided to use C, and Mr. Column decided to use F, then Miss Row will lose 1, and Mr. Column will win 1. Okay, so negative means lose and positive means gain. Okay, so this is simultaneous game. That means the row and column play at the same time, together at the same time. Yeah, so I don't discuss in this class sequential or stackable games. Yeah. Okay, so what happens if we have zero-sum games? Can we also put it as non-zero-sum game format? Yes. Yeah. You can see if you put it as zero-sum game in a format of non-zero sum, then you have two numbers, but they are the same number, only negative of the others. Is that okay? So that's why non-zero sum game is more general, yeah, than zero sum. Is that okay? Okay, so this is the characteristic, yeah. So this is not necessarily competitive, yeah, can cooperate. Okay, and then equilibrium is not the same as maximum, not the same as minimax. And if you inform your strategy before you play, yeah, it may affect uh, the result. You may gain advantage or disadvantage. Yeah? And then you may have a joint plan of action or certain communication prior to the game. Yeah. Then you may get some benefit. Yeah. Later we will play again similar to last week, but different rule. Okay. Okay. So let's see. Uh, this is the most important part that I hope you will practice. Yeah, manually. Yeah, because when you practice this, then you will start to understand how we will do game theory, and it will affect the way of your thinking. And this is what I want you to do. Yeah. Which is to see from other point of view. Yeah. So you need to switch back from the point of view of other player. Okay. So by putting yourself in everybody else's shoes, then you can solve this game. But at the same time, that is very important uh, way of thinking. Okay. So we can have two techniques here. Yeah, one is called iterative domination. So we will reduce similar to zero-sum games last time. Okay, and we will use another technique called Nash equilibrium. Yeah. So when we say strict domination, that means uh, larger than only or smaller than only. Yeah. When we say weak, that means larger than unequal. So weak mean have equality. And the same thing with the Nash equilibrium. Yeah? Strict mean larger than or smaller than, but weak mean have equality. So, okay? Okay. So let's define, yeah? What is the meaning of domination here? A dominant strategy, yeah, is a strategy that give you a higher payoff than all of your other strategy, regardless what your opponent does. Okay, so as in contrast, okay, if we have dominant strategy, then we also have a strictly stupid strategy, isn't it? Yeah, it is a strategy that give you lower payoff than at least one of your other strategy, yeah, regardless what the opponent does. So, of course, this is very bad strategy, so you don't play this one. Yeah. So, how to do iterative domination in non-zero sum games? And so, you will take turn, yeah, to be at its other player's shoes, yeah, until you find a single cell. Yeah, not necessarily you can get, but this is the technique. Yeah. So first you play as row, okay? Because this is two players, so you have two numbers in itself. So you look at the first number in any two rows. Yeah, it's consecutive or not consecutive is okay. Now, if the payoff of one row is always yeah, larger than or equal than the other row, okay, then the larger row dominate the smaller row. Yeah, if you can find domination, then you delete the dominated row. Okay, and then you play as column. Okay, so you look from the other person point of view. Yeah. So you look at the second number because column is in the second number. So look at the second number in any two columns. Okay. Now, if the payoff of one column always larger than or equal than the other column, okay, then the larger column win. Yeah? So the small dominate the smaller column. So if you can find this, okay, you delete the dominated column. Okay. So let's do it with example. Okay. So can you see this? This is our example. So let's play as Miss Row first. Okay, that means you look at the first number, yeah, in any cell. Say you want to compare B and C. Okay, so you compare B and C. What you will see in the first number. So you have 2 and 1 here, right? So 2 is larger than 1, right? 1 and 0. So again, B is larger than C. And then here, 0 and minus 1. Again, B is larger than C. So all cells, B is larger than C. That means C is dominated. So we delete. Is that okay? So you don't care about the second number, yeah, only the first number. When you compare the row, you look at the first number only. Is that easy? Okay, now you compare A and B. Yeah. So again, you compare the row, so you see the first number. Yeah. 2 and 1. Okay, B is larger than A. 1 and 0. Again, B is larger than A. 0 and 2. Oh no. Not always, right? So only these two, yes, but the last one, 0 is less than 2. So you cannot delete. Okay. So because you already compare all the possibility, yeah? So in this case, stop. Now you play as column. Okay. So I just copy the one that we deleted here in the next slide. Okay. So I copy there. I copy. Oops. Here. Yeah. This is I already deleted the row C. Okay. So now you play as Mr. Column. Play in other person point of view. Okay, because you play as Mr. Column, what you will see, the second number. Okay, so let's compare E and F. Okay, so 2 and 1. So E is larger than F. 1 and 0. Okay, E is again larger than F for all rows. In that case, I deleted F. Okay, then I have this reduce K matrix. Until here, is it clear or not? Hmm? Okay, so now, okay, yes, George.
Sorry, sir, but I'm confused with comparing B and C. That you deleted this C, but when you compare the B and A, it's just the same as say same procedure. The first row. Uh, can you go back, sir, to the first
Okay,
slide?
fine. Let's go back to the first one,
Yeah.
and
When
let's.
you compare, sir, the B and C, the two and one, so the two wins, right?
Okay, this
Then
is
the
win,
one,
right?
yes, yes, the
This
one
one
and
also
zero,
win,
yes. But when
and this
zero
one
and
also
I got,
win.
yes, the zero again win. But
Yes,
so we deleted this C.
C,
Okay.
correct.
Then then the next one when we compare the B and A, the next slide, sir.
B and
B
A.
and A, yes. The same
Okay,
thing. The first one and two. The
this
B
is
wins.
win.
Yes.
This is
One and
win, but
zero.
this
This
is
is
not.
yes. Yes.
Then you
This is not.
cannot always win for all columns. Then you are dominated. But if only one of them is not, then
Oh.
it's
Yes, sir. Okay. Okay, sir. I
yeah,
get.
clear, yeah.
Yeah.
So remember the definition of uh, here. That all, yeah, give you higher payoff than all of other strategy. Yeah, the keyword is all. Clear, yeah. Okay, good. So yeah, good question. Yeah. So if you confused, so please ask. Okay. Again, once you have this, now you are playing as Mr. Column. So you look at the second number, right? So say 2 and 1, which one is bigger? This one. 1 and 0, which one is bigger? This one is bigger. So in that case, F is deleted. Okay, and then I get this new reduced matrix, yeah? And next, yeah? So we delete. Okay. I just copy now this matrix into the next slide. Right, so this is the copy, right? So now you play again as Miss Row. Yeah. So in this case, you compare 1 and 2, 0 and 1. Oh, this one is dominated, isn't it? A. Yeah, 2 is larger than 1, 1 is larger than 0. So in this case, I remove. Hmm. So then I get this new reduced matrix. Then I play as Mr. Column. Okay, 2 compared to 1, of course, 2 is larger, so I delete this one. Then I get this one. Oh, I get the result. Yeah, 2, 2. Yeah, so the result is B and D. Is this clear or not? Easy? Okay, good. Yes, yes, Andrew.
Hello, sir.
Yes, yes.
Will will we get the same result if we first eliminate through columns first?
Try. It will
Oh,
give you the
okay.
same result. It will give you the same result.
Okay, okay.
No problem. Yeah, but you can try. Okay, don't believe me, so you try for yourself. Okay, this is science, not so the one of the most important characteristic of science is repeatable, reproducible. Okay, this is not belief. Okay, okay. Next, let's go to uh, the next slide. Represent what you play in the class, last meeting. And this is called personal dilemma. Yeah, this is the variation. There are a lot of variation of personal dilemma. Yeah? I will give you in a moment what is the characteristic. Yeah. So this is the game. Yeah. So in prisoner dilemma, two prisoner, yeah, let's say name it Miss Row and Mr. Column, yeah, being interrogated separately. If both confess, yeah, it's a sentence, say 8 years. This one. Okay. Now, if both deny their involvement in the crime, yeah, it's a sentence just 1 year. Now, if one confess, okay, the one who confess is released, but the other prisoner get 10 years. Okay, so this diagram have different numbers, but the same thing. Okay, so what is the characteristic of prisoner dilemma? Okay. So if you want to create prisoner dilemma, okay, this is the characteristic that you need to get. Okay? These two is the condition of prisoner dilemma. Okay, so how do you get this? You will put a number, yeah, R, S, and T, and P. And what is the meaning of that? Yeah, R means cooperation reward, yeah, or default. T mean temptation, tempted reward. P mean punishment, betrayal, punishment, and then S mean deceive, punishment of succor. Okay, so if you look at this condition, then you know this is prisoner dilemma. Okay. Now, if your number is between 0 and 1, so this is called normalized value, then you need to get this value to be within this range. Okay. So it's very important to understand the condition so that you can actually know, oh, this is the game of prisoner dilemma. Then you know what will happen. Okay. Okay, so let's come back to our technique a while ago, yeah, iterative domination. Okay, you want to practice this using iterative domination so that you will know what is the answer. You can draw here using your mouse. Okay, you can delete. You can participate, right? So what you will do? So you compare the row, right? Yes, yes, George. So if you have 0 and -1, -8 and -10. So which one is domination and dominated? Yes, very good. Yes. And then now you play as Mr. Column. Okay. So what you will compare? Second, yeah. Oh, you get the equilibrium, yeah. So that's why, okay, last week when you play, you get that result, isn't it? You always betray each other, yeah, because the system dictate that, yeah, the rule dictate that you will eventually betray each other, yeah. So interesting, yeah. The equilibrium that you get is the actual behavior of the people given the rule of the game. Now, the rule of the game represents the performance evaluation, right? The way you give reward and punishment. Okay, that means you can design, you can control. That's exactly what planning is about, isn't it? It is something useful. Hmm? Okay, so let's yeah get the the result is exactly what you have. Yeah, so confess. Yeah. So okay, with this, I want to introduce the next concept. Yeah. So this is the concept of Pareto optimal and Pareto improvement. Yeah. So an outcome is optimal, yeah, if it is impossible to find Pareto improvement. So what is Pareto improvement? Yeah. Pareto improvement is the action of making things better without hurting anyone, yeah, or without reducing the trade-off of other metrics. Yeah. So this can be subject, person, or uh, person or organization, or factor, yeah, metrics. Yeah. So a Pareto optimal outcome cannot be improved, yeah, without hurting at least one player. Okay. So to distinguish, yeah, can you distinguish the meaning of Pareto optimal and Pareto improvement? Pareto optimal is a state. Okay. Pareto improvement is an action. Yeah. So Pareto optimal is the state of maximum efficiency where all win-win opportunity has been exhausted. That means uh, you have reached the point where the only way to help someone else to get more is to take something away from someone else. Okay, so this is not actually a good thing. Yeah? The point where all the win-win solution has been exhausted. That's called Pareto optimal. Yeah. So when we say cannot be improved upon here, yeah, that means Pareto improvement. Yeah. It is an improvement. What is that? Improvement is a change where at least one person get a better deal and no one else lose out, right? So if you cannot find anyone any more of this move, of this action, then you are at the optimal point. Yeah. So when we say without hurting at least one player here, that means any further change will be a win-lose scenario. Okay. So if you want to increase one player score, then the score of player B must drop. Yeah, that's the meaning of this. Yeah, let's get more understanding, yeah, in the next slide. So this is a test. Okay. So you ask, can we move to another outcomes? You have choices of outcome, right? Can we move to another outcomes where one player improve without hurting anyone else? Yeah. So if the answer is yes, that means you have Pareto improvement. That's not optimal yet. If the answer is no, that means you reach Pareto optimal. Is there any question with this definition of Pareto improvement and Pareto optimal? So I'll give you example. Uh, say you have two hungry person. Yeah. Are you hungry? Say, let's say Alex and Sam. Yeah. And we have a pizza. Okay. So say the pizza is cut into 8 slices. Yeah. So Alex get 3 slices. Sam also get exactly the same. Yeah. 3 slices also. There are 2 slices left in the box. Okay. So question, is this Pareto optimal? No. Yeah, this is suboptimal. Why? Because you can still give those 2 slices to Alex, or to Sam. Yeah. If you give to Alex, yeah, it will improve his situation, yeah, without taking any pizza away from Sam, isn't it? So it is a free improvement. So this is Pareto improvement, yeah, not Pareto optimal. So assuming the resources is actually hold positive value for all participants, yeah. So all resources must be fully allocated to create a Pareto optimality. Okay, so meaning if you have unallocated resources that equal to inefficiency, yeah. So actually the inefficiency, yeah, is the one that create Pareto improvement. Okay, if you do not have any inefficiency, that means you are already very efficient, then you cannot improve without taking from the others. That is the condition of Pareto optimal. Okay, again, continue with this example. Yeah. So what happened now? We have 8 slices, right? So now you give Alex 5, okay, and Sam 3. Total is 8, right? So there is no remaining. This is the condition of Pareto optimal. Okay? So why? Because if Alex won the 6 slice, okay, it must come from Sam's plate, isn't it? So you cannot improve Alex's situation without hurting Sam, yeah, with giving him less pizza. Is it clear? Yeah. So Pareto optimality is defined as the exact point, okay, where the zero Pareto improvement remain. So that means you already exhaust of the improvement. Okay. Thus, you must exhaust the supply of valuable resources to reach this state. Okay. What we can say about this? Now, if, yeah, if no participants want the remaining resources, for example, yeah, if the pizza is burned, yeah, or if you eat another pizza, if it will cause certain illness, then then this condition is not the same anymore, right? So because distributing them of the remaining will cause some harm, yeah, and yield zero benefit. So this is a special case. Yeah. So, but in general, okay, usually Pareto optimality represent zero waste. Okay, so Pareto optimality is the final state, yeah, where no further free improvement is possible. Okay, so when we say Pareto optimal, that's talking about efficiency, no waste, yeah, no systemic waste. It's not about fairness. Okay, we are just talking about no free improvement left on the table. Is that clear? The difference between Pareto optimality and Pareto improvement. Pareto is the name of person, yeah. So this is the formal definition. Yeah. Say, you have S is the set of all possible outcomes. Okay. And you have outcome X is called Pareto optimal. Yeah. If there is no other outcomes within the same set that make everyone at least as happy as before. This is the mathematical term of this is the utility. And at least one person is strictly happier. So basically, we are saying that the outcome is optimal, yeah, if it is impossible to find any Pareto improvement. Okay, so be careful, yeah. So Pareto optimality sounds like a win-win scenario, but actually this is the opposite. Okay, so actually Pareto optimality is the mathematical boundary where the win-win scenario will go die. Yeah. Say, for example, if the city transit system is Pareto optimal, yeah, then the freelance is over. Okay. So in Pareto optimal state, the progress require sacrifice. Okay. If the city network is Pareto optimal and the mayor demand 10% reduction in emission, then you as urban planner must inform the mayor that passenger travel time will strictly increase. So you cannot improve one without hurting the other metrics. And so it's not something that uh, win-win. Yeah, is that clear? So be happy if you can have a certain inefficiency because you still have chance to improve. Okay, so this is another example so that you get uh, better understanding. Say a company allocate 100 bonus pool, yeah, to two employees, say Alice and Bob, and A and B. So if Alice receive 40, Bob also receive 40. Then you have 20 uh, remaining unallocated, isn't it? Unallocated resources. So this is free improvement is possible. Yeah. If this allocation is not, so this is not Pareto optimal. That is Pareto improvement. But if Alice receives 60, and Bob receives 40, that means no more remaining. Yeah, all the 100 is already distributed, right? So now if Alice won 61, then that extra one must be subtracted from Bob. Yeah. So reducing his total to 39, isn't it? So then you cannot no longer improve Alice outcome without actively worsening Bob outcome. Yeah. So the system has reached a Pareto optimality. Is it clear? Yeah. So I hope using this simple example, I can explain the terminology, yeah, easier. So when you said 80-20 rule, yeah, that's exactly what is called Pareto chart. Yeah. So you have certain things that you do, and just 20 things that you do, you will reach already 80%. Yeah. So, okay. So this is called trivially many and vital few. So if you just do just 20%, you can reach 80% of the result. Yeah, this is based on Pareto optimality, yeah, or Pareto improvement. So, but how about the other 80%? Yeah, that will be difficult to improve. Yeah. So now let's give certain example, yeah, on transport problems. Okay, say you have road network, okay, and you want to expand the road to reduce congestion without adding emission. Yeah. So that is actually, if this is possible, then this is actually Pareto improvement, right? So it will fix the broken infrastructure. Okay, so then you expand the road. That will fix congestion without hurting the emission. So this is Pareto improvement. So you are actually, when you do Pareto improvement, you are actually picking up a free efficiency that already exists, that previously wasted by the bad infrastructure. Okay? So now look at the harsh reality of what is called optimal. Yeah? So when the network is actually become Pareto optimal, okay, then you reach the absolute physical limits of your infrastructure. Yeah? At this state, the progress requires sacrifice. And at this state of Pareto optimal, the only way to reduce congestion further, you will do something that hurt the other metric. For example, you need to bulldoze the neighborhood. You need to increase the emission. You probably need to displace residents and so on. So if the city mandate further, say 10% reduction in emission, okay, then you cannot achieve this without hurting the other metrics. Yeah, for example, converting a car lane to bus only lane. Yeah? Of course, it will strictly increase the uh, car travel times. Okay, so do you understand? Another example. Okay, in urban planning. Yeah. So urban planners often confuse, making things better by making things optimal. Yeah. So for example, you want to create MRT timetable that save energy, without longer wait. So if you can do that, okay, that means the old system was inefficient. Then you can improve, right? So if there is inefficiency, yes, you can do Pareto improvement. Yeah. So, but this is not optimal. Yeah. So the old timetable was simply inefficient. So if you capture this inefficiency, then you have improvement. So when you say I improved it, that means the system is not optimal to begin with. Right. Okay. But when you say it's Pareto optimal, that means you already reached the absolute limit. Okay. So at this point, the only way to save more energy is to force the passenger to wait longer. Example. So a system is Pareto optimal only when you can no longer reduce energy use without forcing passenger to wait longer. Is that clear? Yeah. So it's not necessarily subject or human or institution or stakeholder, can be another metric. Okay. So then we have what is called Pareto frontier. Yeah. So when the free fixed end, so there is a trade-off begin, right? So what is Pareto frontier? That means you have efficient trade-off. Yeah. It's not perfection. Okay. So Pareto frontier means you make a policy choice. Okay. Example here between emission and convenience. Okay. So say when we say Pareto optimal, it will not give you single perfect solution. Yeah. It will give you a list or menu of highly efficient extreme. Yeah. So this extreme is called Pareto frontier, yeah, where the zero resources are wasted. Yeah. For example, yeah, in this example, I give you trade-off between emission and convenience. State A, zero emission, but private no private vehicles. That means nobody is allowed to drive. This is Pareto optimal. Okay. Second extreme, say you have maximum driver convenience, but terrible emission. Again, this is Pareto optimal. Another state, yeah, is the middle ground. Yeah, is a balanced middle ground where neither matrix can be improved without degrading the others. Yeah. Again, this is Pareto optimal. So these three states are Pareto optimal. So we have list of Pareto optimal. So this is called Pareto frontier. Yeah, the list of Pareto optimal extremes. And these are the Pareto frontier. Okay, then you choose, yeah, which of these based on your subjective political choice. Yeah, which choices you are willing to accept, yeah, which trade-off you are willing to accept. Yeah. So as urban planner, you still need to have subjective political choice about which Pareto optimal state that you want to live in. Yeah. Within the objectivity, you still have subjective things. Okay, so this is the computation, yeah, so that you will see here. Say you have this list of outcomes, yeah, between two players, for example, yeah. Then 1, 2, 3, 4, 5, yeah. So let's see how we compute, yeah. Say, let's compare this 10, 0 for B. Yeah, this is A and B. Yeah. So can we move to another outcome where player B improve while keeping player A at least the same 10? Yeah. So at this point, A is 10. So now what to do? You look for other option. These are the Pareto frontier. Yeah. So say you compare with 9, 1. Okay. So if you compare with 9, 1, player A from 10 get worse. Now become 9. And player B get 1 better. So in that case, not valid Pareto improvement. Okay. Again, if you compare this one, 10, 0 with the second one, yeah, 8, 2, for example. So player A get worse, yeah, from 10 to 8. So yeah, player B get better. So again, this is not valid. Okay. Compared to 6, 6, again, the other one get worse, the other one get better, so it's not valid. Compared to 5, 5, again, the same, yeah. So because there is no, among all of this list of outcome, yeah, there is no alternative outcome where B improve without lowering player A. So in that case, 10, 0 is Pareto optimal. So to check the Pareto optimality, you need to check among all the lists one by one. That's why I create the calculator so that you don't need to do all of this. The calculator can do it for you. Okay? But at least you need to know the mechanism how to do. Okay. Let's clean up this one. So how about this one? Comparing 6, 6, which has the largest total payoff, right? With the other outcomes here. Okay. So this is also 6 to 8 improve. Or this one is 6 to 2 reduce. So this is not, yeah. So 6 to 9 improve, 6 to 1 reduce. Yeah? 6 to 10 improve, 6 to 0 reduce. So this is also Pareto optimal, yeah, because no other player can improve without harming the others. Okay. But if you compare one by one, yeah, so you will see that these four numbers, four values are Pareto optimal, yeah, except 5, 5. Why 5, 5 is not? Okay, so you can check, yeah. So how to check? You ask, yeah, can we move to another outcomes where at least one player improve without hurting the others? Okay, look at the, you compare 5, 5 to, for example, 6, 6. So 5, 5 to 6, 6, this is improve and this is also improve. Oh, so both improve, right? So that means this is not Pareto optimal, this is Pareto improvement, right? By definition, Pareto improvement is possible. In that case, this is not Pareto optimal. So the answer is no here. Is this clear? Any question? The mechanic. Yeah? If you can find Pareto improvement, yeah, then this is not Pareto optimal. That's it. Do I confuse you or this is actually helpful? Okay, so this is the definition, yeah. So if you have m by n payoff matrix for two player, yeah, yeah, and this is finite, okay, in any finite set of outcomes, you will eventually hit the ceiling where no further free improvement can be made. Yeah. Therefore, yeah, in every finite games, it is guaranteed you have at least one Pareto optimal outcomes. But this is not happening if you have infinite games, yeah, because they lack of boundaries. So in that case, you can still stretch forever without hitting this ceiling. So look at this way, yeah. If this is finite games or infinite games, yeah. If it is finite games, yeah, or finite games, then it is guaranteed you have at least one Pareto optimal. Yeah. But if it is infinite games, not necessarily. Yeah, this is the example uh, of infinite games so that you will know. Okay. So say you have a simple rule. You have two player. Player one choose X. Player two choose Y. Yeah. Both are positive numbers. Okay. So now the payoff means both player will receive payoff equal to the sum of their number, X plus Y. Okay. Then this is not Pareto optimal. Why? Because for any outcome, there is always Pareto improvement, right? This is the example, yeah. So if player one choose 10 and player two choose 10, so the payoff is 20, isn't it? So if this Pareto optimal, no, because they can choose another value, for example, 11 and 11. The total is 22. Yeah, so both player improve without anyone being harmed. Yeah. That happened because this game using a a set of number that is infinite. Okay, there is no highest number. Yeah, so you can always add 1 plus 1 to both players' score. Yeah, because of this, free improvement or Pareto improvement is always possible. So in that case, the system never reached Pareto optimality state. Okay. So can you distinguish infinite games and finite games? In our game matrix, so this is finite games, because the number of options are clear, only two, and here is only two. Okay, so in that case, at least one Pareto optimal happen. Okay, let us see this prisoner dilemma games. Okay, say from this value, -1 state. Okay, so any attempt to improve Miss row score, say moving to 0, for example, this one, okay, which severely punish Mr. Column, right? So because no free improvement exists for either player, Miss Row and Mr. Column, then this is actually Pareto optimal state. Okay. How about this one? Moving from -8 to -1 actually improve Miss Row by +7, Mr. Column by +7 simultaneously. Because Pareto improvement is possible. If you start from this state, -8, that means this is not Pareto optimal. This represents systemic waste. This is Nash equilibrium, but this is actually waste. So if both players act rationally in their own self-interest, they will both choose confess, right? This one, the equilibrium. This is to avoid the -10 payoff. This lock them into what is called Nash equilibrium of -8. But this state is actually highly inefficient. So the efficient state is actually deny. Is that clear? So can you practice this? Can you find the equilibrium, and is this also Pareto optimal or not? So okay, the technique of iterative domination, isn't it? So what is the equilibrium? If we ask this, is the equilibrium also Pareto optimal? So you check first the equilibrium, and then only check the Pareto optimality of that cell. Okay. You can do it here if you want. So first you check the row. For example, 50 is higher than 40, 30 higher than 25, but this 0 is not higher, so you cannot find the row. Let's check the column. 7 higher than 5, 1 is higher than 6, you know. How about this one? 7 and 0, 1 and 0. Oh yes, this one is dominated, right? 7 and 0, 1 and 0. So in that case, you can delete this one, correct? Okay, now you have the deleted, so you compare the row. Okay, 50 and 40, 30 and 25 dominated. Yeah, this one you can delete, correct? Now you compare the column 7 and 5. This one is deleted, so this is the result. Yeah, clear, yeah? Then after that, you compare this one. This is Pareto optimal or no? Yeah. So then you compare to other choices here. Yeah. So 50 to 40 reduce. This one also reduce. Yeah. So in that case, what? Pareto optimal or not? Can both reduce and reduce. So yeah. Can you improve this one? 50? There is no higher than this one, right? How about 7? Can you improve? Yes, 7 can improve to 60. Yeah. But this one is reduced. So cannot. So in that case, what? This is quality optimum, yeah. That clear? Yeah. So that's actually Pareto optimum. Okay. So this is the uh, story if you want to get the result. Yeah. So 57 is actually Pareto optimal. You compare one by one to all other outcomes. Okay. Yeah, very long comparison. Okay. So uh, if you want to check all, so these two outcomes is actually the Pareto optimality. Yeah. Okay, up to here. Any question about Pareto optimal, Pareto improvement, is the iterative domination? Is this clear or not? Am I too fast or that's okay? Okay, okay, good. Then let's talk about one of the most important, yeah, what is called Nash equilibrium, yeah. Okay, there. So Nash equilibrium, yeah, is a state of the game, yeah, in non-zero sum, yeah. It's a state of the game where no player prefer different action, yeah, if the current action of the other player are fixed. So you hold the action of one player, and then the other player move to different action or not. Okay? This is the definition. Yeah. So it's a strategy combination. Yeah. It's called Nash equilibrium if no player have incentive to deviate from his strategy, given that the other player also do not deviate. Yeah. This is quite complex. Yeah. So what is the technique to do? Yeah, this is called best response method. Yeah. The technique is you hold one player strategy constant, okay, and then you ask, yeah, if the column strictly play certain strategy, what is the row's best response? And then repeat from the other player point of view. Yeah. So repeat this for every possible strategy for both players, then you will get the result. Okay, so this is the algorithm. Yeah, you can do it by hand. Yeah. Okay, the algorithm is only for 2 players. Yeah. So first step, yeah, say you find the row best response. Yeah. So for each strategy available to column, okay, then you identify which strategy give row highest payoff. And then you mark this payoff, either you circle them or you put them into a list. Yeah, so let's name this list 1. Then you play as another player. Yeah. So in this case, for uh, column best response, you can find, okay, for each strategy available to row, okay, identify which strategy give column highest payoff. The same thing, right? But the other point of view. And then you mark them or and then you put them into list 2. Okay. And then if you want to find the Nash equilibrium, you find the intersection between these 2 lists. Yeah, it's a set intersection. Okay. Then you get a Nash equilibrium. Yeah. So if the intersection is empty set, that means that game matrix have no Nash equilibrium. Yeah. So Nash equilibrium can be 0, 1, 2, or many. Yeah. So not necessarily exist and not necessarily unique. Okay. Now, if you have more than one player, yeah, then you do it one by one. Yeah. So you fix strategy for all the other player. For example, player 2, 3, and so on until n. Then you find player 1 best response. Okay, and then put that into list 1. The same thing, now you play as player 2, and you find the player 2 best response. Then you fix the strategy for other player. And then you store this as list 2 and so on. So you repeat this process for every player. Okay, then you find the intersection. Okay? So that intersection is called Nash equilibrium. Yeah. So let's give example. Say if you have 3 player, this is related to your assignment. Say in the traffic, in the intersection, okay. Say you have 3 player A, B, and C. Okay, and each have 2 choices, either to proceed, yeah, or to yield, isn't it? So then how you find the equilibrium? First, you fix, say, the player are A, B, and C, right? So you fix B and C choices. Okay. So if B play P, proceed, and C play Y, that's yield, what is A best response? Yeah. And then if you fix A and C choices, yeah, if A play P, yeah, proceed, and C play Y, yield, what is B best response, and so on. Yeah. So in this case, because you have 2 choices and 3 players, that means you have 8 possibilities, isn't it? Yeah, not just 3. Okay, so then you find all of these possibilities, okay, and then you find the equilibrium. Yeah, equilibrium in the scenario, okay. For example, A yield, B proceed, C yield, and so on, where no individual driver will regret their choices, even what the other 2 driver did. Yeah? So when we said this, that means the game is actually simultaneous. Yeah? It's not sequential. So I want to touch a little bit, yeah, just 1 or 2 slides about sequential games. So sequential games mean the player do not act simultaneously, but they move in a specific order. Yeah. So in that case, you don't use the previous algorithm, yeah, but you use a new algorithm called backward induction. So in that case, you assume, yeah, row play first, and then column will observe this move, and then again, column turn, yeah. For every possible move of row could make identify the column rational best response. Yeah? Very similar, yeah. But the difference is in simultaneous game, you just hold fixed. Yeah? In here, you assume certain player move first. Okay, so as the result of these sequential games, yeah, it often yield what is called first mover advantage. Yeah, so that means when the player who are first will force the second player into specific predictable outcomes. Yeah. So I will give you example in the battle of sexes. Okay. What is battle of sexes? Here. Yeah. So this is a conflict between a man who want to go for a soccer games and a woman, yeah, they are dating. Yeah. So who want to go to ballet? While selfish, they are actually deeply in love. Yeah. So this is a love story. Okay. So if necessary, they want to sacrifice their preference to be with each other. Right. So Miss Row and Mr. Column. Yeah, so this top and bottom represent soccer games and ballet. Right. So can you find the Nash equilibrium? Yeah. So here, if you look at this, so let's play as Miss Row. Yeah. So you look at the first number. Okay. You first, what you will do, you find domination, right? 2 and 0, 2 is larger, 0 and 1. So you cannot find dominant row. How about column? 1 and 0, 0 and 2. So again, you cannot find dominant row or columns. In that case, you need to use the best response, yeah, algorithm. So what to do? So you create the 3 diagrams like this, yeah. So if Miss Row select top, yeah, if Miss Row select top, what is the best response of Mr. Column? See, I will write down here. So if Miss Row selects top, yeah, you fix Miss Row choice. What is the best response of Mr. Column? So 1 and 0, which one bigger? 1. So in that case, TL, yeah. So this cell win, isn't it? Okay. How about if Miss Row select bottom? What is the best response of Mr. Column? With comparing 0 and 2. Of course, 2 is larger than 0. Oh, in that case, you have this one, BR. Okay, so this is list 1. Okay, list number 1. So TL and BR. Is that okay? Okay, now let's clean up this one. Now you play, yeah, assume as Mr. Column, yeah. I'm not playing first, but so Mr. Column, say, assume we'll use left. So what is the best response of Miss Row? So if Mr. Column use left, then Miss Row comparing between 2 and 0 will select the L, right? And what happens if Mr. Column select right? What is the best response of Miss Row? Comparing 0 and 1, 1 is larger. So this one, PR again. Yeah. So this is list 2, right? Number 2. So the intersection of list 1 and list 2 is actually TL, yeah, and PR. So in that case, you have two equilibria. Yeah, this is the equilibrium. Is this clear or not? This is the Nash equilibrium. Yeah, yeah, this is the Nash equilibrium. So in battle of the sexes, yeah, you have two equilibria. Yeah, and these are actually also Pareto optimal. Yeah. So to compute the Pareto optimality, you compare all this with other choices. Yeah. So I listed here, okay, how you compute the Pareto optimality. Yeah. So you can read by yourself. Yeah. So if there is no other outcome that improve one player payoff without decreasing the other player payoff. Yeah. No Pareto improvement. Yeah. So what is the meaning of first mover advantage? Yeah, look at this. Yeah. If row commit first, okay, row will choose top, forcing the column to choose left. And the outcome is 2, 1. But if column commit first, okay, that means the column will choose right and forcing the row to choose bottom. So the outcome will be different. Yeah. So this is sequential move. Yeah. That means what happened? You have what is called the power of disclosing strategy. Yeah. Yeah. So those who are have reputation, reputation important. Yeah. So if you have a reputation of inflexibility and you disclose first, yeah, what you will say. In this case, you will gain advantage. You just say, I'm going to do this. So you make up your mind. Do whatever you want. So in that case, yeah, uh, Miss Rowe will end up selecting what Mr. Column want or the other way around also. Is this clear or not? So you, by disclosing this, yeah, you are making the simultaneous strategy become simultaneous game become stackable or a sequential game. Okay. So let's compare now. Okay, what's the difference between Nash equilibrium and Pareto optimality? Yeah. So in this table, yeah, we try to distinct between Nash equilibrium and Pareto optimality. Yeah. So Nash equilibrium is something that gives you the prediction. Yeah. Using Nash equilibrium, you will know what will happen. What will happen if selfish individual will do? Yes, George.
Sorry, sir, for this question, sir. But for the battle of sexes, who wins, sir? The one who wants for ballet or the one for soccer?
There are two equilibrium.
Yeah, if there's two equilibrium, it means there's no decision. You mean both of them did not decide to go for ballet or go for soccer?
Yeah, you will not get to this 1-1 or 0-0. Yeah, you will either go to soccer or to ballet. Yeah, these two possibilities. Yeah, but that's why I'm talking about this closing strategy. Who win is the one who fell first.
So this table, sir, is not really the solution to that.
Yeah, the
That
prediction is not really about what will happen uniquely. Yeah, because this game have two equilibria, right? So when you ask that question, you assume you have one equilibrium. But in this game, you have actually, yeah, in this case, you have one, but in this game, you have two. So that means not necessarily one of them. So you can either select this one or the other one, depending on the information. Yeah. So if you disclose first, yeah, then you will win. Yeah, this is the interesting part. Yeah. Actually, yeah, because information creates something different result. Mhm. Right? Remember, yeah, Nash equilibrium can be zero, no, not exist. That means you cannot predict. Yeah. If that exists, okay, not necessarily unique, not necessarily only one. Mhm. Okay, but part of optimality in finite game like this, you will get at least one. Okay, so I answer your question. Okay, but here, so using this Nash equilibrium, you can predict. Yeah, if you can find Nash equilibrium, then you can predict this is what will happen. Okay? But Pareto optimality is your tool to evaluate. Yeah, what is the perfectly efficient system look like? Okay, so but be careful. Okay, be careful. Pareto optimal does not mean fair. Example, if the mayor own 100% of city wealth, land and resources, and the citizen own 0%, is this fair? No. Is this Pareto optimal? Yes. Why? Because the only way to help the starving citizen is to take resources away from the mayor, which will hurt the mayor payoff, right? Okay, so be careful. Yeah, Pareto optimality has absolutely nothing to do with fairness, equity, yeah, or ensuring group are not disadvantaged. Okay, so Pareto optimality only measure the efficiency, yeah, meaning zero waste. Yeah, so by using resource fairness, yeah, no group disadvantage, you are confusing Pareto optimality with the concept of pure egalitarian. And so, say in this case, this is the example. Yeah. So if you want to use Nash equilibrium, okay, so then the developer and the buyer will adjust, yeah, the zoning rule, yeah, to create the layout where neither can boost the profit alone. So this is the Nash equilibrium. Yeah. So you create competitive pricing. Pareto optimality is useful for public policy. Yeah. So you want to guide the efficiency, yeah, ensuring that all the available resources are fully utilized. Okay, but be careful because you reach the optimality. That means further improvement will require explicit trade-off. Yeah. Okay. So you want to design or evaluate the system that maximize collective benefit. That's the meaning of Pareto optimality. Zero waste. Yeah. Not necessarily fairness. Yeah. Uh, okay. So this is another example. Maybe you want to practice. Can you find the Nash equilibrium of this? Yeah, the story goes like this, yeah. So a big company, okay, will spend a lot of expensive, yeah, to educate the public, right? Then the small company simply can imitate, yeah. So without ruining the big company sales completely. But on the other way around, if the small company introduce them at the same expense, then the big company just imitate, then the big company will dominate the market, right? So, and these are the values, right? If if both educate, the big company will win, yeah, 5 and 1, yeah. If the big company educate on the same product, and this one imitate, so you get 4 and 4 the same, yeah. So this one, if the big company imitate and small company educate, then the big company win. Yeah, 9 and the small company lose. Yeah, if both imitate, then 0, 0. So can you find the Nash equilibrium? Can you find the domination? So if you cannot find domination, then you use best response. Oh, let's say 5 and 9. 9 is bigger. 4 and 0, no. So you cannot find the row domination. How about column? 1 and 4, 4 is larger. Oh, uh, you can find, right? This is 1 and 4, 4 is larger, -1 and 0, so this is also larger, so you can delete this. Yeah. In that case, you can uh, now play as row, so this one you can delete. Yeah. So you get educate, imitate, yeah, as the result. Yeah. Is this clear or no? Okay, yeah, you see? Mm, next one. Yeah, how about if you want to use NAS? Yeah. So you, yeah, if you want to use NAS, you can also get exactly the same result. Yeah. So uh, you create list one. So first you say that, okay, big player will educate. What will happen? Yeah, if this is fixed, what column will do? Yeah, what column will do? So between 1 and 4, which one? 4 winning, yeah? So this is winning. How about if a big player will play imitate? Between -1 and 0, which one win? This one is winning. So, okay, this is list one. Okay, and then uh, now you said we fix a small player, educate. Okay, so then you select between 5 and 9. Which one is bigger? Or 9? Yeah, and then you said this one. Uh, Now small player play imitate. Okay, which one will you choose? 4 and 0. Okay, this one. Okay, so between list 1 and list 2, what is the intersection? This one. Right. Okay, so you get exactly the same result. Yeah. Different technique, the same result. So do you know how to get the Nash equilibrium using best response? Or you want to practice again? Is this clear or not? Yeah? Okay, then let's practice. I have many. Okay, for you to practice. Oh, how about this one? There's no dilemma. Yeah, we already did iterative domination. So now is your time to find the Nash equilibrium, yeah, without iterative domination, but use the best response. What you will do. Anyone want to volunteer to um, explain? Yeah, in here. I want you to make sure that you understand. Yeah. Good. Yes, George. Go.
So do I need to write? I will just crash out.
Yeah, yeah, you
Yes.
just
Okay.
play.
Okay. I will compare the row for this one first.
Okay. So which one you will fix?
-1 and 0. So 0 is the bigger one. Then -8 and -10. So -8 is the bigger one. So I will crash out this row.
You are using iterative domination, right? No, please use best response, not iterative domination. We already did iterative domination.
I thought I will just crash out, sir.
No, you already did iterative domination, right?
Okay.
Let's do the best response algorithm. Okay, let's try again. So what you will do, you fix one. Say you fix. Yeah, Miss Row will choose deny. Example. What will happen? What is the choice of Mr. Column? If Miss Row say will select this one, the first row, what Mr. Column will do? Huh?
The column will choose confessor because
Yes,
0 is
default.
higher than
Very
-1.
good. Now I will mark here. Yeah. What will happen if Miss Row fix? Okay, it fix. Miss Row will select confess. What the column will do?
The column will still choose confess because negative 8 is higher than
Correct.
negative
This
10.
one. Okay, this is list one. Okay, list one is DC, yeah, deny confess, and then CC, yeah, confess, right? Okay. Now let's play as here. You fix this one, yeah. So if Mr. Column fix, it will play deny. What Miss Row will do? Compare between -1 and 0. Which one?
Uh, the 0.
0. Very
Select
good.
confess, yes.
Okay. Now, if Mr. Column
So
fix the confess, what Miss Row will do?
still confessor.
Still confess this one.
Yeah.
So the list is CD, right? And then CC. Is that correct?
Yes, yes, sir.
Okay. Now the intersection between these two lists is this one. Correct.
Yeah.
Yes.
Yes, sir. Confess,
So
confess. So
confess.
negative 8, negative 8.
Yes,
This one.
this is the Nash equilibrium. Easy or not? Hmm. The only simple technique is you need to check one by one. If Miss Row play this one, what column will do? And if Miss Row play this one, what column will do? And the same thing, if Mr. Column play that one, what Miss Row will do, and so on. Okay. With that, you can already get the Nash equilibrium. Yeah, it's not difficult at all, right? Yeah, just comparing. Okay. Okay, so let's go. Yeah, this is the result. Yeah, CC. How about this one? What is the what is the Nash equilibrium? No. What is the Nash equilibrium? So you fix one, or they are the same. So yeah, if you fix that, this one, 0 and 0, right? The same. If you fix this one, you will select this one. If you fix this one, again it's the same. If you fix this one, you will select this one. Yeah. So you have actually PD. Yeah. This one is the Pareto. AC is also a possibility if you don't put a strict. Mm. If equality is also point, so that's why we have weakness and strictness. So this is another game called Matching Pennies. So the story is you have two players, okay? So each of the two players will select either head or tail, okay? So if their choice different, then Miss Row will pay Mr. Column by 1. If they are the same, then Mr. Column will pay Miss Row by 1. Yeah, so this is strictly competitive. Uh, is this zero sum? Yes. The sum in itself is one. So this is strictly competitive. Yeah. Zero sum game. So can you find the Nash equilibrium of matching pennies? Anyone? Hmm. Yeah. None, right? You cannot find the intersection, and so you get zero mass equilibrium. Yeah. So this is the one of the example that there's a game that you will find no mass equilibrium. Yeah. So so this is another game famous. We call it hawk or dove. Yeah. So in business, in politics, yeah, sometimes you will use this kind of analogy, isn't it? So what is the analogy? There are two animals fighting for some prey. Yeah. So each will behave like dove, peaceful, willing to lose, or like hawk. Yeah. Always want to win. Okay. So you can see, okay, dove is loving, peaceful, and the hawk is always want to win. Okay. So can you uh, find the mass equilibrium? This is interesting, right? So how often the real world situation become like this? Yeah? Maybe you see between your office mate or your classmate, yeah, some are doing hawkish, yeah, the other one is playing like tough. Why we want to find mass equilibrium? Because when there is a situation like this, you know what will happen. Yeah, you can predict the behavior. Yeah? If you can find the mass equilibrium. In matching penny, you cannot find. You know, that means that game is unpredictable. How about this one? Can you find the Nash equilibrium? Yeah. So if you if Mr. play tough, what will happen? What Mr. Column will do? 3 and 4, so 4 in, yeah. Mr. play hawk, okay. What Mr. Column will do? 1. So play tough, right? If Mr. Column play fix, yeah, to play tough, what Mr. will do? This one. And if Mr. Column play hawk, what Mr. will do? This one. So you have two equilibrium, isn't it? Yeah, this is the equilibrium. Yeah. So this is interesting. Actually, the equilibrium is interesting. Why? Yeah, if one, this is what will happen, right? If one play hawk, the other one will play dove. Yeah. If and etc. Yeah. So if one play dove, the other one will play hawk. That's the actual situation will happen. Because if both play hawk, both will lose. Yeah. Of course, the best one will this one. Yeah. If you go to tough, that's the best. But that will not happen. Yeah. This is what is the probably Pareto optimal. Yeah. But uh, the mass equilibrium is these two. So for uh, coordination and cooperation, you have different games. This is called coordination game. Okay, using this game matrix, yeah, the player will benefit from cooperation. Yeah, so if you need to coordinate your action, so you need to create the game matrix, something like this. Now, that means if the player hide or move, hide the move or lie about what she is planning to do, yeah, she will get penalty. Yeah. So coordination game happens in many situations in real life, including traffic signal. So in traffic signal, it's the same thing. Yeah. So this is actually coordination game. So if both goes, will accident will happen, right? Uh, if one go and the other one stop, and the one will go will get benefit, move, and the one will stop, don't move, right? So uh, if both stop, get also lost. Yeah, this is actually your assignment later, yeah. And another situation is if two worker demand raise salary, yeah. If both will say a company only have two workers, yeah. So if both demand raise, yeah, both will get raise. Okay. But if only one demand raise, the one who demand raise will get fired, and the other one get nothing. Yeah. Of course, if both do nothing, then both will get nothing. So, yeah. So by putting this kind of qualitative uh, payoff, yeah, then you can also assign any number that represent that qualitative payoff. Okay. Okay. Let's practice this one. This is also coordination game, but this is called dangerous coordination game. First, you find the domination. So then if you cannot find domination, you do best response algorithm. Yeah. Okay, anyone who did not recite, so you can try this. Yes, Andrew.
Hello, sir. I'll try
Ah,
to answer.
mhm.
So, using iterative domination, I think uh when comparing the row A and B, it's there's no dominant
Mm,
row and there's no dominant column.
So you cannot use
So
iterative to be.
okay, I'll do the best response
Yes.
first.
A.
In this A column, A row column will pick C,
Yes.
and in row B, column will pick D.
D. Okay.
In column C, row will pick A,
Okay.
column D, row will pick B. So
Okay. That is
Nash
what
equilibrium
as
is
equilibrium. Yeah.
AC and DD.
Very good. Easy, right? It's clear. Very good. So you know how to do. Okay. So you can predict already the response. What will happen? Yeah. Easy, yeah. Uh, everyone can do. You have a question about this? Yeah. You see. So let's do the next slide. Oh, this is called a game of chicken. Yeah. So it's a race car. Okay. So the two cars starting from it's a duel. Okay. So then they will move very fast toward each other from opposite direction. Okay. And the one that actually uh, swerve uh, lose, right? And then the one who pass will shout chicken like that. Huh? Okay. So and the one who serve will become the object of contempt. Yeah. So this is an old story. Yeah. So the schematic is something like this. Yeah. This is actually often happen in real life also. Yeah. So if both continue, both die, right? Accident happen. So -3, -3. Yeah. If both swerve, yeah, actually both safe, yeah, but lose space. So 1-1. Okay. And if one continue, the other one swerve, the one that continue will gain reputation of brave, something like that. Yeah. So and the other one gets 0, yeah, not die. Okay. So what is the Nash equilibrium? Anyone? Try? Who did not play? Diane, Lester, Daniel, come on. Are you still there? So if Mistro fix to continue, what column will do? This one, swerve. Yeah. If Mistro said swerve, what column will do? Continue. Right. If Mr. Column say continue, what Mistro will do? Swerve. And if Mr. Column says swerve, what Mistro will do? This one. So this is the Nash equilibrium. There are two. Yeah. Yeah, I repeat actually the same thing, the same technique, yeah, but different values, yeah. By introducing this, I hope you can understand the technique. And for scissor, rock, paper, yeah, there is no equilibrium, yeah. So there is no Nash equilibrium, yeah, but there is some Pareto optimality if you change the king matrix. So now I want to introduce you with this game. Yeah, this is proposed by Jean-Jacques Rousseau. Yeah, one the hero in France Revolution. Okay, so the story goes as simple as this. Yeah, there are two hunters. Yeah, they want to choose either to hunt stag or hare. Yeah, so this is the drawing, either stag or hare. Okay, so uh, the stag is a big, so the reward is massive, okay, but require two people to catch. So if one person attempt to hunt the stag alone and the other one actually hunt hare, the solitary stag hunter fail, get nothing. Okay? But hare is a small reward. Okay? So it can be safely caught by one person, regardless what the other person does. So this is also talking about the trust. Yeah? There are two trusts here. Yeah? Uh, Based on that Nash equilibrium, can you find? The Pareto optimality is clear. Yeah? So 10 is Pareto optimal in this case. Yeah? And without the trust, you will see the uh, Nash equilibrium is actually this two, right? But with the trust, you will get Pareto optimal. Yeah? Without trust, you will select this one. Okay, knowing this, okay, let's play. Yeah? Let's play. So the class will be divided into two. Let's play this one. Is that okay? Are you still there or not? Similar to last week game. Wait. So you will select X and Y in, okay, let me open the Excel similar to last week. Okay. Let me get this slide. Yeah. So again, the purpose of the game is to reveal your way of thinking. Okay? I want to test this class have enough trust or not. Yeah? You can also negotiate and cooperate on betray. And it just came, right? So, and don't feel bad if your team is betrayed by the others. Yeah. So let's divide the class into two teams. Yeah. Okay. We are only six. So 3-3. You can select your own team. Okay, so let's break into two teams and let's play just 6 rounds. So at round 3 and 5, so you will discuss among the team. Okay, so again, the objective is the same like last week. Okay, you want to get the best score among your team, and you select either X or Y. Okay, so you chat to me, and then X mean trustable, yeah. Y mean cheap. Okay. So this is based on start hunt. And the number is exactly the same as a while ago in the slide a while ago. Okay, so this is the rule of the game. If all team, you have two teams, right? If all team select Y, okay, all team get 5 points. Yeah. If all team select X, then all team get 10 points. Yeah. If there's a mixture, okay, so in the vote, so those who vote X will get 1, those who vote Y will get 8 points. Yeah. So that's exactly the start hunt value a while ago. Okay. So shall we play? Okay. How many are you? Oh, only 5. Okay. So 2 and 3. You don't have group mate, so you join other group. Uh, do you want me to give you the group? Okay, I will open. I will open room. Is that okay? Wait, how to open? Breakout room. Okay. I will create just 2 rooms. Make sure that not just so either 2 or 3. Yeah, not just one in one room. Open. Oke ya. Diane, are you still there? What's the group vote for round 1? Two. One, two, three, 4, 5, 6. Okay. Hmm. So what is your group vote for round one? Okay, you can DM me one of your representative. Okay. How about not sure. Round one. Okay. Andrew is round two, right? Round two. Right. And then how about group one? Oh, okay. So this is your result. Okay, I will share with you the result. Okay, both will select Y. Both will select Y. So what's the result if both select Y?
5 points.
Oh, if both select Y, you will get 5 and 5. Okay. Okay, so let's go for round two. You want to discuss again, or you just discuss it here in the room or here?
Uh,
It's up to you.
Sir, we already have a decision, sir, from 1 to
Okay,
6.
good. Okay,
Oh,
so
sir.
okay, then I will close all the room then. Okay, so tell me your decision for round two. Mhm. Again, for round two. For round two, you are selecting Y again. Okay, this is not good. Okay, so before round three, you can discuss to make a non-binding agreement among the teams. Right? So what do you think? Are you sure you want all 1, 2, 3, 5, 6 with all Y? That means you will betray each other. Are you sure? Go discuss among yourself between the teams. Isn't that cooperation better? It's rather strange, right? You are selecting
Uh,
5 over 8 and 10. What make you
uh,
select Y?
we
Go, go. Go ahead. No problem. You can discuss. Done or
So far, no motion from our team, sir.
hmm?
No motion yet.
No motion yet.
We're not yet. We're still consolidating our decision internally, so
Okay.
we're at a decision gridlock.
Good. But that's not logical. You can either win 8 or win 10, but you choose 5.
I guess this is like how distrust looks like. But I think what I can propose to represent Group 1,
Hmm.
perhaps we can try to cooperate for one round. Is
Hmm.
that something that you would be keen to accept, Group 2?
Hmm. Yeah, non-binding agreement. But what do you think?
Hello. So
Yes.
I think the outcome of this game does not go beyond the course. So why not make a legacy and we'll just pick X all throughout.
Yeah, just for round 3
And
only. Just for round
or
3.
just for round three, let's say if you pick X, we'll still pick X until the end. Or we'll just take the joke on us if we we lost. But uh this is wait, I'll ask my group mate if that's okay. Is that okay, Lester?
Right.
Yeah, it's okay with me.
Eh, Because
Since
imagine this video or lecture will be uploaded in YouTube, right? So we will have a legacy that this is the cohort that got the most points across all uh 258
Yeah.
cohorts. So imagine that. That's
Logically,
amazing.
logically, right? Your
Yes,
choice of
that's
5 is
my
wrong.
case. I think. So for uh for next round we'll pick X.
Okay?
Duly noted.
Duly noted. Okay, so remember this is not a binding agreement, so you can still betray, no problem. Again, this is just game, right? Just for fun. So let's go round 3. Okay, you tell me, DM me, okay, so that you'll get a simultaneous game, yeah? The purpose. Okay, and okay, super. So you get this result. Okay, this is your result of round 3. It is share. Wow. Right. So you start to cooperate. Okay. Again, this is non-binding agreement. So how about for round 4? For round 4. Okay. I'll close.
Thank you for staying true to your word, Group 1, Group 2.
So for round 4, what you will choose, let I can copy round 4, you get that. And Daniel is, did you choose round 4? Okay, good. So the result is round 4. Yes, X and X. Yeah, so another 10 and 10. Right. So round 5, you want to discuss again among yourself?
Hello.
Yes.
So
Hello.
there's a risk in the last round that the other team will pick Y, but on our side we'll just pick X again. So it's up to you.
If you want to win, but at this point it's tie, right? So
Yeah, I think Atay is win for having the most points
yeah, for the system, but not for your
across
group.
all. Yes. If there's a ranking among all the groups that tried this game, we'll both teams win.
Right. So non-binding agreement. So let's go to round 5. Okay, round 5. Mhm. Round 5. Okay. Oh, round 5 is also get the result. Still tie. So no winner. Yeah. Okay. So last round, think about it. Round 6. TM me round 6. If you want to win, you need to betray. Right. Go ahead. Round 6. Just to decide X and Y. Easy, right? Right. And round 6. Okay. Andrew, what is your room? 1 or 2?
2, sir.
2. Okay. Andrew is 2. So you get X and Y. There. So what is the score if different? So if there is different, okay, those who make X get 1. The other one get 8. Yeah. So group 1 win, yeah, at the end. Yeah. Uh, this is what will happen, yeah. So if you play a lot of round, but majority will get almost similar with this YY or XX. Yeah. But if you want to win, okay, that means this is what happened to the actual company, right? So even if it is trustable company, yeah, if they are in corner, okay, in the last situation, probably they will change the decision, right? So that's come with the next slide, yeah, about threat and credibility. This is related to this result, yeah. Yeah, thank you for playing the games. Yeah, what's your feeling? uh, don't don't feel bad. Yeah, this is just games. Okay, just for fun, right? Okay, so I will close this part and let's go to the threat and credibility. You download the slide there. And this is interesting. Okay, this is part of game with information. Yeah. So we will apply game theory, okay, to create trust or credible or to create a threat, right? So how to create a credible threat and non-credible threat? Yeah, just one of the application of game theory. Yeah. Oops. Okay. So information will play an important role in threat credibility. Yeah? So this is what I explained in the beginning. Yeah? So most grade school teachers actually have self-interest, not informing the parent about children misbehave. Yeah? But why? Because it will upset the parent, and they know it is usually teacher's fault. Yeah, not acting as a real teacher. Yeah, but the children does not know this. Yeah, so this is asymmetric information, right? Then the teacher will threaten the children to behave well or else report to the parent. Yeah. But if the children knew, yeah, the teacher's self-interest, then they will decide not to behave actually, right? Yeah. So then this is another case study. Yeah. Yes. Oh, you cannot see the slide. Can you see? Okay, thank you. So say a parent threaten the daughter, yeah, because she got pregnant, for example. Okay. It will disown the daughter if you get pregnant. Yeah. So the question is, should the daughter believe that threat or not? Is the threat credible or not? Yeah. So if she knows the parent actually love her, okay, of course, it is not credible threat. Yeah. But if she believe that threat, yeah, uh, why it is a non-credible threat? Because she believes that threat is just made to improve her own welfare, right? So, and if she really get pregnant, yeah, it will not be the self-interest of the caring parent to actually carry out that kind of threat, right? So this is called non-credible threat. Okay. So question is, using game theory, can you demand for raise in your workplace? Right. So the question is, why should your boss give you a raise? Yeah. Is it why is it in her interest to be nice to you? Yeah. Interesting question. Right. Then you have any chance at getting a raise, yeah, if your company actually will be worse off without your labor, correct? So in that case, yeah, the best chance obtaining a raise, yeah, is by convincing your boss that you will leave if you don't get the money. So you create a threat, right? So, but the question is, your threat is credible or not? Okay? Why should your boss believe in your threat? That you are really needed, actually. Okay, let's analyze this situation. Okay, so you ask for raise, right? And then the boss have two choices, to give you the raise or not to give you the raise. So if the boss give you the raise, so the boss will keep you, but give you say 20,000 more. Okay. If the boss did not give the raise, yeah, then you have two choices, right? Either to quit or not to quit. So what happens if you quit? The boss will lose you. If you don't quit, the boss will keep you at the old salary, isn't it? Okay, we can put numbers here. Okay, and I will show you there is asymmetric information between you and your boss. Okay, so say uh, say using zero-sum game. This is we apply both sides. So say your boss value your work, say 150K. Okay, and then you demand raise from 20K to 80K. Wow. Okay, because the oil price is so high. So at this point, because of the Iran war, right? So this is the game matrix. Zero-sum games, right? So from your boss point of view, either to give raise of your salary or not to give raise. So if give raise and you still quit, the actual value is 150, right? So it will lose 150, but it will gain, giving you the salary, the 80, and minus 20. So that means minus 90, right? But if the boss did not give raise and you still quit, so that losing is 150 plus that 80, right? The raise. So that minus 70, isn't it? And if the boss give raise and you don't quit, so the total is 50. If the boss not give raise and you don't quit, so positive 70. This is the computation of game matrix. Is that okay with this? Next. But you don't know that 150, right? So you don't know how much your boss value you. This is your boss thinking. This is the game matrix within your boss thinking. But how about you yourself? This is your payoff because you don't know this value. Okay, so you think this way. Okay, this is asymmetric information, right? So if you quit, and your boss give raise, okay, so you lose 100. If you quit and your boss did not give raise, you lose 80, right? And if you don't quit and your boss give raise, this is almost impossible, you get 100, okay? And you don't quit and your boss did not give raise, you still get 80. Okay. Now, based on these two game matrix, asymmetric information, okay, both payoff are actually zero-sum games, isn't it? But now we can combine these two. When you combine these two, okay, the two game matrix have different information. Okay, so if you can find, because this is zero-sum game, so you can find the saddle point, right? So again, you might think the best way in your case, based on your game matrix, is not to demand any raise. Okay, but from your boss game matrix, the boss think that you may quit if he did not give raise to your salary. So it's different decision, right? Because asymmetric information, it's not the same information. Then what happens if you combine? So combining this, meaning you know the information about your boss, and your boss also know about your payoff matrix. So you just combine the two into a new game matrix with these non-zero sums. Do you understand now how you get from zero sum to non-zero sum games, yeah, based on asymmetric information. Yeah. Based on this, so you can find the Nash equilibrium. Yeah. So you can simply delete based on domination. So the result is not quit and not keep race. Okay. So this is the Nash equilibrium. Yeah. You will not quit and the boss will not give you any raise. And that's what will happen. Yeah. If both knows the information from both sides. Yeah. It's different decision because of knowing information. A while ago, asymmetric, now symmetric. Now you know both side information. Okay. Now you still want to get the race based on this game. Okay. Without credible threat, yeah, this is what will happen. Yeah, you will not quit, and the boss will not give you any raise. In that case, you start to give a threat. Okay. So how you will create a credible threat based on game theory? Yeah. So you show that you have no alternative. Yeah. Or other company offer higher. Right. So, okay. So the best way to make your threat credible, yeah, is to prove to your boss that other company will pay you higher salary based on your demand. Yeah. So that's threat become credible. Yeah. By removing the alternative, yeah, so this is the story to know the war. Okay. So General Cortez bring the soldier and then he burned his own seat, yeah, so that uh, the soldier will boost their spirit, yeah, in order to eliminate the choice. Yeah. So in other way, if you want to get the race, yeah, you pretend to be crazy. So you tell everyone in the farm that you will definitely quit, yeah, if you don't obtain it. Yeah. So you put yourself in a complete humiliation if you are denied the money. Yeah. So the point is you create some pain to yourself. Yeah. If you don't get that raise. Yeah. Then the game matrix change. Yeah. By putting yourself certain pain, then this value become very high. Yeah, say 1,000 minus 1,000. Okay. With this, the game matrix, you can see, yeah, comparing credible threat and without credible threat. Okay. So you will see without the credible threat, you will not quit and will not get raised. Yeah. And with credible threat, you will surely quit if you will not get raised. Yeah. So this is what happened. The threat become credible because you will surely quit. Yeah. So now with that, now if you put now into a new simultaneous, yeah, both of you, boss, your boss and you know about the whole situation. Yeah. Now the K matrix changed into non-zero sum. Yeah. Now instead of that, now you will get minus 1,000 here, right? Yeah, so you input back this K matrix here into the non-zero sum games. So the equilibrium become this one. Okay. So you will keep and you will not get raised. Yeah. So the point is by securing reputation, yeah, as being honest, actually you increase your credibility. Yeah. So honest behavior arise more from self-interest rather than morality. This is the main point. Okay. So based on self-interest, okay, you will become honest. Yeah. Not because of religion, not because of morality. Yeah. So this is what happened. Yeah. There are kidnapping problem in the southern of the Philippines. I don't know still there or not. Yeah. So kidnapper will demand ransom. Yeah. But the victim family should comply only if paying the ransom actually increase the chance that the victim will be released, isn't it? So, so if the victim family will pay a ransom only if they believe that chance, yeah, actually to free the victim, yeah, increase. So now, how about the kidnapper? The kidnapper planning in the long-term game, yeah, they need to play to have reputation of being honest. They are kidnapper, not good people. Okay. But if they want to have a long-term game, they need to keep reputation of being honest. So if they want to do repeat kidnapper like Abu Sayyaf, so they need to tell the victim family that in the past they released the victim. Yeah. Only if that demand were met. Funny. Yeah. So honesty is not come from good things, yeah, but come from self-interest in the long-term game. Surprising. Okay. The same thing with business. Yeah. Why you will see a lot of advertising, paying advertising very expensive, right? So why they do that? Yeah, because they want to get credibility. Yeah, advertising is to create the brand, right? So say this is the name of the company, Acme, for example. Yeah. So the business will get a greater incentive if they treat their customer fairly. Yeah. So this is the game matrix. Yeah. The game tree. From the customer, they either go to that Acme company or not to go. Yeah, if not to go, everyone gets 0. If they go to that company, the company have two choices, either to exploit or to treat fairly, right? So if the company treat fairly, so the company get 1,000, and the if the company exploit, the company will get 1,000, the customer lose 2,000. Okay, but if the Acme company treat the customer fairly, the Acme will get only 100 and the customer get 100. Right. So which one the choice? Yeah, if you look at the uh, K matrix and find the equilibrium, that depends on two possibility. Yeah, if the company want to play short term or long term. Right. So if this is the if the game is played only one, and this is the game matrix, yeah, the Acme will benefit it exploit the customer. Yeah. So, but if they play long term, okay, so then Acme will treat the customer nicely. Okay. So, but be careful, yeah. No matter how nice the Acme treat and promise the customer, okay, at the end, yeah, if they think this is the almost bankrupt, for example, yeah, like your game a while ago, yeah, stuck in hard a while ago, right? The last point, someone will betray, yeah. So they will play short-term game. Yeah, if they are almost bankrupt, they will play short-term game. So yeah. So in that case, they better lose credibility in that case. Okay. So this is the last equilibrium of short-term game, right? So, but if the game is played repeatedly over long term, yeah. So Acme will be better off if it play honesty. Yeah, so 100 is better than 0. So remember, yeah. So this one, yeah, completely selfish and greedy company will profit from treating the customer fairly and honestly. Yeah, that's why they invest in brand name, yeah, to prove their trustworthiness. Yeah. So now we can explain why people pay very expensive for advertising. Yeah. So again, repeated play does not guarantee honesty. Yeah, if the firm is about to face bankruptcy, yeah, they may cheat. Yeah, even though in the past they has been honest. Yeah, because the game matrix a while ago. Okay, so again, this is another example. Is it you want to play nice or you want to play mean? Yeah, with your competitor. So if the competitor play nice, okay, both of you will get 1,000. Yeah. If the competitor play mean, you have two choice. Yeah, play nice or to play mean. Right. If you play nice, the competitor will get 2,000 and you get only 100. But if you play mean, both of you will get 0. Right. So then put this into the matrix, then you can calculate the Nash equilibrium or saddle point. Yeah. So this is if either play simultaneously or sequentially. That's also different, right? So since the competitor move first, rationally you will play nice. Yeah, will get 100. Yeah. If the game is played simultaneously, then you will still play nice. Yeah. The question is how you will force the competitor to play nice. Yeah, so that you will get 1,000. Okay. So yeah. So now, if the competitor thought that you were interested in seeking revenge, yeah, that means you win irrationally, yeah, by being mean, yeah, with that, okay, and not rational to maximize your payoff, then he will play nice and you will get 1,000. And actually, this is a paradox. Yeah? So a person who rationally cares only about money will make less than someone who irrationally make more diverse goal. Interesting lesson from game theory. Okay, by pretending to be irrational. Okay, so then you will get something. Okay, see, you will get this, right? So this is called benefit of insanity. Yeah. So being perceived as irrational can be advantageous. Yeah. So your competitor will make her decision not based upon whether you're actually interested in seeking the revenge, but whether she thought you were interested in the revenge itself. So revenge is actually irrational desire to harm others who have injured our loved one or us, right? So the optimal strategy is to adopt, yeah, with respect to legal vengeance, yeah, to convince people that you insanely attach to vengeance, okay? When if someone did violate your legal right, then you will rationally evaluate whether to sure or not, actually. Yeah. But pretending to be insane will make the game matrix change. Okay? So this is the summary. Yeah. So you only fear if it is credible threat, right? So you only trust if it is credible promise. Okay. So remember to do long-term game. Yeah. So repeated player. Uh, if you want to have a repeated player, then you will increase your credibility. So you tell, look, I don't come here just for one-time gain. I want to stay for a long time in this game. Then you increase your credibility, isn't it? Okay. So these are the way to increase your credibility. Yeah. So showing that you have no other alternative, showing that you have no choice but to fight. Yeah. Or you create honesty reputation by creating brand name, or telling your move publicly, or perceive that you will behave irrationally. Yeah. So strange thing, yes, but these are the something that we can take out of all those numbers. Yeah. So thank you very much for today. I hope you enjoy the lesson of game theory, with the games. Yeah, and don't feel bad. Yeah. Again, this is all just game. Yeah. Is there any question, any discussion that you want to say before we leave? We still have 2 minutes. Uh, your assignment, I don't know, when is the presentation of your project? Is that next week or next week? Oh, yeah.
April 30, sir. Next week.
Next week. Yeah. So please submit the presentation one day before and prepare the group project presentation. Okay. So next week we'll discuss the reverse game theory. Yeah, the reverse of game theory. So how you control. Now this is very important for planning, isn't it? Knowing the game theory, this is called mechanism design. How are you going to control? Yeah, to create the system. Okay, that's more interesting, right? Okay, and we can also discuss about this. Okay. Okay. Any question, discussion? So what did you get from today's lesson? Nothing. Okay. Oh, okay. This is the time. So, yeah. Thank you very much.
Thank you, sir.
Yes.
Bye, sir.
So, bye-bye. So, see you next week. Okay.